Hello dear students, let us solve some numerical problems related to radioactivity. First question is, two radioactive samples A and B have equal number of atoms initially with half-lives 3 hours and 9 hours respectively. Compare their rates of disintegration after 18 hours. Here, solution to question first. Given for sample A and sample B, initial number of atoms are equal, that is n naught of A is equal to n naught of B, and their half lives are T half of A is equal to 3 hours, T half of B is 9 hours, 3 hours and 9 hours respectively. Then after T is equal to 18 hours, we have to compare find the ratio of their rate of disintegrations, that is R A upon R B, which is now we know rate of decay, which is equal to minus dN upon dt is equal to lambda into n, and n can be replaced by n naught into half power n, where n is number of half-lives, means total time divided by half-life time. Here n for A will be equal to 18 hours upon half-life of A. This 3 hours means 6, and n of B will be equal to 18 hours upon 9 hours is equal to 2. Therefore, the required ratio will be equal to R A upon R B, which is, from this relation, lambda of A, n naught of A into 1 by 2 to power n A upon lambda B n naught B half power n B. n A and n B are equal, therefore they cancel out, and lambda is equal to 0.693 upon T half. Therefore, lambda can be replaced by 0.693 upon T half of A divided by 0.693 upon T half of B in place of lambda A and lambda B, into 1 by 2 to power n A is 6, and n B is 2. Here Na is 6 and Nb is 2. 0.693 cancel out and we get Ra upon Rb as this goes in the numerator. So Tb, T half of B upon T half of A into half power 6 minus 2 means half power 4. Now putting the values of T half A and T half B, we get T half B is 9 and T half A is 3. Hours cancel out, hours cancel out, and half power 4 means 1 upon 16. This gives 3 upon 16 as the required ratio. Next, question number 2a. The sequence of stepwise decay of a radioactive nucleus is D emits alpha particle and becomes D1, which emits beta particle and becomes D2. If the atomic number and mass number of D2 are 71 and 176 respectively, what are the corresponding values for D? Means we have to find the atomic number and mass number of nucleus D. Now, solution to question 2a. Here we have nucleus D emits alpha particle and becomes D1. D1 emits beta particle and becomes D2. D2 has atomic number 71. D2 has atomic number 71 and mass number 176. We have to find the atomic number and mass number of D. Now, as we know, alpha is equivalent to helium, and we know alpha is equivalent to helium 24 and beta is equivalent to electron. Therefore, we can write D Z A emits alpha particle and D2, so D1 and D1 will have Z minus 2 as atomic number and A minus 4 as mass number. Now after beta decay we get D2. Here when D1 emits a beta particle, that is electron, its atomic number increases by 1, so it will be Z minus 2 plus 1 and mass number will remain unchanged, means A minus 4. Here A minus, or here Z minus 2 plus 1 is equal to 71, which gives Z as 71 plus 1 means 72. And A minus 4 is equal to 176. Therefore, A will be equal to 180. Therefore, the atomic number of nucleus D is 72 and mass number is 180. Now next question. From the activity time graph for radium, find the decay constant. Solution to question 2b. From this graph, it is clear that the activity becomes half of the initial activity after 16 days. Therefore, after 16 days, activity becomes half of initial activity, where A is activity minus dN upon dt. Therefore, half-life time period will be equal to 16 hours and decay constant lambda will be equal to 0.693 upon T half. Lambda will be equal to 0.693 upon T half means 16 days, which gives 0.043 per day. Next question number 3. What percentage of atoms is decayed after 5 half-lives? Justify your answer with calculations. Now, solution to question 3. We know the number of atoms remained after n half-lives periods is given by n is equal to n naught half power n, where here n is equal to 5. Therefore, n will be equal to n naught half power 5 means n naught upon 32. Therefore, number of atoms decayed will be equal to initial number of atoms n naught minus number of atoms remained, means n naught minus n naught by 32, which is equal to 1 minus 1 upon 32 means 31 upon 32 n naught. And therefore, percentage of atoms decayed will be equal to n naught minus n naught by 32 upon n naught into 100. It is 31 upon 32 n naught upon n naught into 100, which gives 96.875%. Next question number 4. thorium 92 232 emits 3 alpha particles and 2 beta particles to form radon. Find the values of Z and A. Z and A. Solution to question 4. Given this is thorium having atomic number 90 and mass number 232 and mass number 232. It emits 3 alpha particle and 2 beta particles forming radon. Atomic number Z and mass number A. We have to find Z and we have to find A for radon. We know alpha particle is equivalent to helium 24 and beta particle is equivalent to electron. Therefore, 90 minus 3 into 2 plus 2 into 1, because alpha particle emission decreases atomic number by 2 and beta particle emission increases atomic number by 1. So, this will be equal to Z. Therefore, Z will be equal to 86. Similarly, this minus 3 into 4 minus 2 into 0, so 2 and 232 minus 3 into 4, 3 into 4 minus 2 into 0 will be equal to A. Therefore, A will be equal to 220. The activity of a given radioactive sample emitting alpha particles is 540 becquerel and the kinetic energy of alpha particles is 8.6 into 10 to minus 14 joules. Find the number of alpha particles emitted per second, number of alpha particles emitted in 1 hour and the rate of energy emitted. So, solution to question 5. Here given for a radioactive sample which is emitting alpha particles. Activity which is R minus dN upon dt is given to be 540 becquerel. We know 1 becquerel is equal to 1, where 1 becquerel is equal to 1 decay per second. Thus, number of alpha particles emitted per second will be equal to 540 BQ means 540 decays per second. Next, number of alpha particles emitted in 1 hour will be this much multiplied by 3600 second. Number of alpha particles emitted per hour will be equal to 540 into 3600, which will be equal to 1.944 into 10 to power 6 decays per hour. Third part, rate of energy emitted will be equal to rate of decay into E. Rate of decay is 540 decays per second, and E is the energy associated with each alpha particle decayed, that is 8.6 into 10 to power minus 14 joules. So we get 4.644 into 10 to minus 12 joule per second means watts.